In this screencast, we're going to talk about interpolating polynomials in regression. We're going to try and find a parabola or a line. A parabola will pass through the 3 points here, or the line will best approximate the trend in the data between the points. Really, the idea is we want to learn how to do regression, which is if you've collected a bunch of data points, how do you get a line which best approximates the trend in the data points? That's what we're going to do, and we're going to do it by studying what's called interpolating polynomials and then getting out regression. So let's begin. The idea is, first, we want to try and find a parabola. Well, parabolas are of the form y equals a x squared plus bx plus c. This becomes complicated to generalize, so we're going to first standardize the notation. I'm going to rewrite this as y equals a naught plus a1 x to the first plus a2 x to the second. The reason for doing that is then if I want to add in a cubic, I could put an a3 x cubed, or a quartic, a4 x to the fourth, or I could just keep on going. Or in summation notation, I could write ai x to the I starts at 0 and then heads up to whatever number you want. We really are only going to focus on the parabola, so we can ignore this for now. But this will generalize to all dimensions easily once we've learned how to do it with a parabola. So the idea, I've got 3 points, and over here I have 1, 2, 3 unknowns. 3 points, plug them in, that should generate 3 equations. So if I put in 0, let's replace each x with 0. We get an a naught plus a1 times 0 plus a2 times 0. And then I get out the number 3. When I plug in minus 3, I get a naught plus, we're putting in minus 3, a1 times minus 3 plus a2 times minus 3 squared. And I get out 0. Now, if I put in the number 2, I get an a naught plus a1 times 2 plus a2 times 2 squared, and I get out negative 1. This is now a system with 3 equations and 3 unknowns. We're going to put it in matrix form. So in the a naught column, I'm going to write a 1, 1, 1. Those are the numbers in front of a naught. In the a1 column, I'll write a 0, minus 3, 2. In the a2 column, I'm going to write a 0, 9, 4. Notice this column is just the square of the numbers in that column. And then I'll put the y values, the 3, 0, negative 1, in the final column. So here's our y's. Well, this system, if you reduce it, I will let you do the row reduction with your own calculator. I just want to show you the idea. Out pops the solution 3, negative 4/5, negative 3/5. Well, this is a naught, this is a1, and this is a2. So a naught is the first number. I'm going to just write y equals 3 plus the next number is negative 4/5 x, and then the next number, negative 3/5 x squared. We just found the parabola we were after right here. And now the next question is, how do we get the line? To get the line, we're going to do something very, very similar. We're just going to write y equals a naught plus a1x. We want a line that passes through those 3 points. There is no such line, but we're just going to try and repeat everything the same anyway. Plug the points in. Well, that's the exact same thing as what we did above, just remove the x squared column. Just remove that column of the matrix. Just remove that column of the matrix. So I'm going to actually just write that down right now. I'm going to write 1, 1, 1. The x values, 0, negative 3, 2. Eliminate that column, and now I'll write the 3, 0, negative 1. If you reduce this, out pops the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. This bottom line says 0 equals 1. No solution. Well, why does it say there's no solution? Because there's no line that passes through those 3 points. It's not possible. So the problem here is we have 2 unknowns, but we have 3 equations. Too many. This system is called over-determined. And so what we want to do is we want to somehow remove some of the information from the problem, but still solve it. Someone discovered that the transpose of the matrix right there does the trick. So I'm going to take the transpose. So take this matrix and we'll make the first column the first row. The second column we'll turn it into the second row. And multiply the matrix by this original matrix multiplied by the transpose on the left. When you do that, out pops a matrix that now only has 2 rows. The matrix is 1 plus 1 plus 1 is 3. 1 minus 3 plus 2 is negative 1. 0 minus 3 plus 2, negative 1. And then 0, 9, 4, 13. Over here we get a 3 plus 0 minus 1 is 2, and then minus 2. This system, if you row reduce, becomes 1, 0, 0, 1, and then 12 19ths and negative 2 19ths. Well, wait a minute, this should be A0 and this should be A1. We took a system with no solution, multiplied by the transpose, reduced, and then obtained a solution. This 12 19ths is our A0. So our function, our line is y equals A0 is 12 19ths plus A1, which is minus 2 19ths, x. That is precisely the equation of this line we obtained in the picture. I just want to briefly show you how to do this with Cramer's rule, because I think that Cramer's rule is an efficient way to solve it. So we take the determinant of this matrix, that's 39 minus 1, which is 38. I put the 2, negative 2 here, and leave the negative 1, 13 in. So that's 26 minus 2, which is 24. And then I take the 2, negative 2, put it in the second column, and leave the 3, negative 1 there. So that's minus 6 plus 2, which is negative 4. And now I take the 38 and divide each of these numbers by 38. Well, this is precisely negative 2 19ths, and that's 12 19ths. And we obtain the solution using Cramer's rule. That ends the screen.